Just a minute. Just a minute. Oh, yeah, sure.
He was a destitute runaway from his older brother's printing shop in Boston.
Alright, today we're going to talk about static electricity. And then next class we'll talk about current electricity. And the lab today we're going to do the test equipment lab, tools, equipment, ESD. And I think that's it. Tools, yeah. Basically how to use a digital, this DMM, power supply, some of the advanced features, hopefully. Before we do that, I have to call the roll and make sure everyone's here. So when I call the roll, if you could please just show me your homework, that'd be great. And if you don't have a notebook, you can have one of these for $2 so I can replace them. I bought these so that if someone didn't have one. Again, just record everything in your lab notebook so that you have a nice sequential order of everything that happens in the class. Okay, Clarence West? No homework? Okay. Corey Adams? Okay. Okay, thank you. Gary Nichols? No homework. The book's free online. Yeah, it's on Moodle. Robert Lambert? Robert Lambert? Dakota? Good job. Benjamin. Now we have a break between class for questions and things, so we'll have plenty of times for questions. And I would like to request that before class, no questions, because I'm like, you can see how busy I am. So, just as a courtesy to me, like 15 minutes before class starts, please don't try to ask me any questions. I can get with you like during the break. Every 15 minutes we'll have a break, and during lab today we'll have a lot of breaks. So there will be plenty of times for questions. Benjamin Bettinger. Benjamin. Frederick Garrison. Seems like a lot of people dropped off. Christopher Drew. Okay, thanks. Donald Fillerman. No homework? All right, thanks. Appreciate it. Jesse Dalton. Is that everybody? Oh, you know what? I must have another sheet. Oh, okay. Sorry.
138 there, don't you?
Yeah, I got the wrong one. Sorry about that, guys.
Well, at least you're done for your next class.
Yeah. Corey Adams. That's better. Okay. Yeah. Okay. Sorry about that. 133. Okay. Okay, that's good. Okay, yeah, that's good. I knew something was going on strange there. But okay. Austin McCoy. Okay, good job. John Witherspoon. Never here. James Campbell. Leon Elkins. Oh, thanks. Christopher Drew. You got homework?
Yeah, I just started it.
Okay. Gary Nichols. Gary Nichols. Don Philemon showed me his already. Jason Lanny. Oh, okay. Probably, yeah. It's okay. Liz Parker. You what?
I'm not a show from the 90s.
Okay, thanks. Dakota, saw yours already. Jesse Dalton. Jesse Dalton? Oh, that's right. Saw yours already. Santuan Dalton? Santuan? Thanks. Clarence West. Clarence West. Oh, you didn't have yours. Sorry about that. Benjamin Bettinger. Benjamin Bettinger. And Kevin Prevett. Okay, good. Thanks. And Tyler Thornsberry. Okay, appreciate it. Yeah, looks good. Okay. All right. Okay, if you guys would take your books out, then we're going to go through the book today. Section 1.1 through 1.3. Okay. So what if I have a signal, or let's go over some key terms really quick. What is logic level 0? What does low logic level mean? Without, yeah. 0 volts. Yeah, logic. Yeah, that's right. The lower of the two voltages in a system. How about what does positive logic mean?
Positive logic means that high is represented by binary number 1,
Mhm.
low is binary number 0.
Yeah. So if you had an output of a gate, so for example, and you had like enable with a bar on top of it, that would be considered logic low, low level. Because low is in this case considered enabled. If this is going to a processor or going to something that is enabled, then the signal goes low. And that's usually indicated with the bar over the top of it.
What would high be?
What's that?
What would?
Well, if you had a signal coming in here and you had this signal called disable, for example. Disable, there's no bar across it. So when this goes high, it'll disable the part. That's logic high level. It could have been called enable too. You know, whatever, it doesn't really matter. This could be called something different. You know? But yeah, this is considered high level logic because it's enabled. It's assumed when you name it like this, that this device here is going to be enabled when it's high. Otherwise, you put a bar there. And many times when you have, like if you have this device here, and you have this output, this is called the enable bar. It usually has a bubble sometimes on the devices to say that it's, and then they'll name it differently with the bar over the top of it. Okay.
Bar over the top means low logic.
Yeah, it means not. So enable with a bar means enable not. So it's kind of like going enable and then putting it through an inverting gate. Enable becomes enable not. This is a not gate or an inverter. So. Okay. And if we have our diagram here that you guys drew, 0.8 to 5, you know that if you have a voltage inside of here, that's going to be undefined. Up here, this is considered high. This is considered low. Anything outside of that is undefined.
You said it would either given a 0 to a high or low randomly.
What's that?
You said it would give a high or a low randomly.
It could give you a high or low. Undefined means that it's not really defined means you don't know what it's going to be.
Sometimes it'll flip flop.
Yeah, undefined. You can call this unknown. You can call it undefined. You can call it question mark. It's going to be something. It's going to be interpreted as something when it gets sampled. It gets sampled by a clock. If it goes into a microprocessor, if this is a microprocessor, well, the microprocessor has a clock, and on the edge of the clock, usually the positive edge, sometimes positive and negative edge, it'll get sampled, and at that time, it needs to be already slewed to the level that it needs to go. And we'll get into more detail of that later. For now, we just need to know. Okay. I think we're good on that. Okay. So let's talk about number systems. If you go into section 1.3, remember there's a quiz on Friday, so I'm basically going to give you the answers to the quiz today, so I recommend you write down what I say.
Thanks.
Yeah. Okay. So how does the binary system work? Well, the binary system, you have bits. And a bit is a 0 or a 1. Okay, those are called bits. And of course, 0 represents nothing. 1 represents 1 unit of something. And so there's also positional notation with binary. If you want to create numbers bigger than 0 or 1, the way you do it is, this would be 0 if you wanted to make 1. Of course, you could go here. Now, what if you wanted to make something other than 0 or 1? Then you would add a 1 here and a 0 there. Just like in our decimal system, if you have 9, you go all the way through 8, and if you want to increase the number, and you have 1 through 9, basically symbols. Actually, you have 0 as well, so we need to start with 0. So you have 0 and 1, dot, dot, dot. We also have 2, 3, 4, 5, 6, 7, 8, and 9. So that's decimal. Deci means 10. So you have 10 symbols. We call those symbols. And the Arabic system of numbers, the Roman numerals number system was, if you had a 10, then you add, you had a 1, you had 10.
You have 5 to be.
Well, you had C, right? You had L.
You have a V between the I and the.
Oh, you had V, that's right. You had 5. M. Can't remember all of them, but if you wanted to create you just kept stacking these things together. Like this is 10, 20, 30, whatever. Well, that's not a positional system because it doesn't, well, it's kind of positional because depending on where you put, like if I wanted to have an extra one here, or if I wanted to subtract one away, then it was sort of positional. But it wasn't, the Arabic system was a little different. And we use the Arabic system of numbers, which is now a universal language, but their system was positional. So if you have a 1 over here, in this position, it represents having all of those numbers, which is 10. Okay, so this represents having 10 plus 9, or 20. That represents 2 10s. This represents 3 10s plus 8. So it's the same over here, except that we're having a base 2 system instead of a base 10 system. So base 2 system, we have 2 symbols. Okay, 2 symbols, 0 and 1. And so this represents, what do you think this represents?
10.
What position do you think this represents? 2. If this over here represented 10, then this, and this is a decimal system, then this position represents 2. Okay? This position represents 1. If there's something there, then it's a 1. The problem is you can't put a 2 here to represent 4. Because you don't have 2 in this system. You only have 2 symbols. Okay? You have a symbol of a 0 and a 1. So if I want to represent 3, how would I represent 3? This position is 2, this is 1.
Both of them be 1.
Put another 1 where the zero's at. Now you got 2 plus 1. Right? Just like over here, you got 3 plus 8 is 38. So that's the binary system. Now, what do we want? Now we have a 3-bit number. This represents 3. What am I going to do? What am I going to do if I want 4?
1 0 0.
1 0 0. So now, what position do you think this next position is going to be? 3? 4. What's the next position going to be? How are you doing that? What are you doing? Multiply by 2 makes sense, right? How do we multiply by 2 like this? Now, if we say this is, let's say that this is we index these. We say this is the LSB, least significant bit, which we say it has bit 0 is what we call it. Bit 1, bit 2, bit 3, on up. So this is the LSB, this is the least significant bit, this is the most significant bit. Now this is the Arabic system, and the Arabs, they write from right to left, and so is numbers. We don't really pay attention to the fact that we write numbers. We probably write our numbers from left to right, but really they're supposed to be written from right to left because they're going from lowest to the highest. But we write them backwards. But so this is where the number starts, and it increases as it goes this way. Okay? Okay, so if we wanted to have... So what number is this? Now, in digital systems, many times when you do design, nothing represents 0. And you can think of it having beads. I usually, for this experiment, I have like a little game that I bring, and I'll try to bring it. Actually, I do have it. We'll do a little lab exercise later. But think of these as little beads or something that you have. Okay, so the presence of a bead is represents by 1, and nothing just represents nothing. So imagine counting really a long time ago, and so the 1, you have a 1 here, and you have a 1 there. Everything else is 0. So what number is that?
9.
That's 9. Yeah, so you can put the zeros there if you want. How would you make this number 10?
Erase the 1 under the 1 and put a 1 above the 2.
Yeah. Okay. So I think you guys, who's kind of confused by this right now? You're confused with it? Okay. Let's do something. One of the most basic things you can do here. First off, okay, how is this 1, 2, 4, 8? You guys talked about how you just multiply it by 2. Well, 1, 0, 1, 2, 3. We call this the we call this the index. So this is the 0th bit, the first bit, the 2nd bit, and the 3rd bit. It's kind of confusing because there's 4 bits. Now, how do we wind up with these weights right here? Well, the way we do the weight is we say that this is 2 to the 0. Okay, this has a weight of 2 to the 1. This has 2 to the 2, and this has 2 to the 3. Now, who's okay with that? Everyone's okay with that? Who's not okay with it? Does anyone understand what this means? I think there's a lot of people that don't understand what this means. What does it mean when you have an exponent? This is called an exponent. Okay? So if you have a number and you have an exponent on top of it, 2 to the 1, it just means you multiply 2 by itself 1 time. So 2 to the 1 is just 2. If you have a 0 up here, it says take this number, this base number, this is the exponent, this is the base, okay? It says take this 2 and multiply it by itself 0 times. So what if you multiply 2 by itself 0 times? You have nothing. Okay. So 2 to the 0 is 0, which we just said it had a weight of 0. I'm sorry, 1. In math, anything to the 0 power is what? 1. Okay, so I messed that up. That's 1. Anything to the 0 power, by definition, is 1. And that's just one of those things you kind of have to just say that exists.
It's one of the rules.
Yeah.
Right.
I don't really know why that's true. Anything to the 0 power is 1. Okay. So that's one little nuance we have here. But the rest of them make sense. I promise. So 2 multiplied by itself 1 times is 2. What does this mean? 2 multiplied by itself twice. That's what that means. So that's 2 times 2 equals 4. 2 multiplied by itself 1 time is 2. 2 multiplied by itself no times. Actually, you're not actually doing anything. By definition, has to be 1. So 2 to the 0 by definition. So we use 3 things that say that by definition. By definition. I can say that one doesn't make a whole lot of sense to me, but that's just the way it is. The rest of them do make sense. Okay, number 2 to the 3. 2 to the 3, what does that mean? That means 2 times 2 times 2. So really, if you think about it like this, anytime you increase the exponent, all you're doing is multiplying the previous number by 2. That's all you're doing. Okay? So this is binary. This is a base 2 system. So base 2 means what? Binary. If you look up the word binary, it's probably going to be some Greek word that means 2. That's all it means. It just means 2. Decimal means deci. That's where we get the word December, because there used to be 10 months. January and February used to not exist, and so we used to have 10 months. December was the 10th month. Okay? Decimal system. So 10 to the 1 is what? 10. 10 to the 2 is 100. 10 to the 3, 1,000. Now in the decimal system, we're kind of going a little bit off. But I wanted to let you know that I just talked about the binary system. We need to talk about the decimal system a little bit. In the decimal system, yes, it's how many times you multiply by 10, but what effectively it means is how many zeros you have. Okay? So 10 to the 2, you have 2 zeros. 10 to the 3, you have 3 zeros. 10 to the 1, you have 1 0. But that doesn't work over here. Over here it's different because you don't have the decimal. It just happens to work out because this is the number system that we have. We only have 10 symbols, so it just happens that way. Okay. Now, so the first basic thing we want to do with the binary system that we just learned, and that you guys are going to be tested on Friday, so you're going to be experts by then, is how to count, right? How to count in binary. Let's say we have a 4-bit number, okay? This is called the least significant bit, LSB. This is called the most significant bit. Please remember that and write it down. This is the least significant bit. This is the most significant bit. If you have a billion bits, this is still the most significant bit over here. Now this one's not the most significant anymore. The one on the right, because we're using the good old Arab system, the right takes precedence. That's where they start writing. Okay? MSB. Okay. So how do we count in the binary system? Well, the way we do it is 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Okay? In fact, get out a piece of paper right now and see if you can finish this table really quick. I'm only going to give you like 30 seconds, so I'm going to run by and see if you guys can do it. How do you fill out the rest of this table? How far can you go with 4 bits? How far can you count? Good. Good. Have you done this before? That's good.
Just read it this way.
Okay, that's good. Yeah. Okay. I see. Now, if you're struggling with this, I want you to just remember that this is just like the this is 1 0 0 0 1 0 0 0 0 1 0 1. as you're doing this, I mean, you've been using numbers your whole life, but you probably haven't really thought about what you're doing when you're counting with numbers. But that's what you're doing. Remember, when you go from 9 to 10, remember, what are you doing? There's two things you're doing when you go from 9 to 10. You're saying, first off, there's zeros in front of that. You're just omitting. That's the first thing. The second thing is when you go from 9 to 10, you're 6, 7, 8, 9. You don't actually have a 10. You only have 10 symbols. What you're doing is you're going all the way back up to the beginning with this number, and you're taking this number and incrementing it. Okay? So you're overflowing this number, and you're incrementing the next number. That's what you're doing. It's the same thing with binary. Okay? The same exact thing. 0, 0, 0, 0. So only here, then you got one number. You only got 2 bits. So you go 0. You increment this number. Okay. Now you can't increment anymore. So what do? You overflow it and you increment that one. Okay. Now you want to go to the next one. Okay. Well, you always start over here. You always start incrementing this. So what are you going to do over here? 10. You're going to go to 11. You increment the least significant bit on the right. Think Arab on the right. You start from the right. And then you go 12, 13. So you're incrementing this number until it fills up, and then you increment the next number. Okay? So what do you do here? You always increment this number. That's all you're doing when you're counting. Always increment the least significant bit until you can't increment anymore. Then you overflow it, and you increment the one right next to it to the left. So 0, 1, 0, 0, 1, 1. Now I need to increment this one, but I can't increment it. Okay? So how am I going to do that? So I'm going to overflow it. I'm going to increment this one. I can't increment that one. So I'm going to overflow. So I go back to 0 and I overflow it to here. Now, in essence, what you're really doing is you think of carry. You're carrying it over. Okay? So how many numbers are you going to have for a 4-bit number?
16.
0, 0, 1, 1, 0, 1, 0, 1. Yeah. Yep, that's right. Yeah, you should have 16. 1, 2, 3, 4, 5, 6, 7. 16. Okay. Yep. Count, make sure you have 16. No, right here, you increment the LSB. So you incremented all of these numbers. When you went from this to this, you just incremented all these numbers. You can only increment the LSB from one step to the next. So erase that one that's a 0. That's going to affect everything else. This has 500. I think that one. Oh, okay. This one is 1. This one right here is 0, 1, 1. This is 0, 1. Yeah. You increment this one, so you overflow that one. And then actually, there's a 60 goes there. Yeah, but at least you got that right. That is something. You just get that. Okay, so everyone come up here and most of you got it. Most of you got it. For those of you who didn't, too much stuff up here. Okay. This is pretty much how it works. This is the easy way to do it. Put this thing on there. That thing actually seeing that? Yeah, there we go. Okay. Here's kind of an easy way to do it. This is 0, right? That's 1. Now how do I go from 1 to 2? If you want to position, say, okay, these cups, it's going to be 2, 4, 8, 16. Okay, so this would be 2. Okay, now I want to have 3. I wouldn't move it here, right? I say, okay, 2. Or 3, I'm sorry. That's 0, 1, 2, 3. Now I want 4. Well, you...
Take them one.
Yeah, if you increment this one, then it's going to go away. If you increment that, it's going to go away. So what you do is that's 4. Okay? So you're basically taking this one. What do you take to think of a carry? So if you increment this or you overflow this one, you're going to go, had 0, you had 1, now you're going to go with 0. You're going to carry this over to there. Okay? That gives you 2 in this cup. Okay? So that's, what is this? This is 2. This is 4. This is 1. So 2 and 2 is 4, which is the same as that. Is that confusing?
Yeah. That's if you have
1.
more than
This is think of this as being, here, let's write some numbers. Give me a piece of paper. Anyone have a piece of paper? Piece of paper. Okay. This makes it easy. 1, 2, 4, 8. Okay. I want to do 1. Okay. Now I want to do 2. Add another one. Always start at this side of the cup. Okay? That's 2, right? But we can't have, the rule is you're going to have 1 bead in the main color cup at a time. That's the rule. Okay? So how are we going to make this 2 a 2 with only one main color, with only 1 bead in the cup?
take one out, overload them, just do one.
Okay, that's the same thing, right? Okay, now you always have to put the beads in on this side. Okay? That's 3. That's 4, but you can't do it. But it is 4. That's 2, and that's 1 and 1. This has a value of 2, this has a value of 1, this has a value of 1. Because it's in that cup, it has a higher value. Okay, so one way to combine these is, okay, move this over there, right? But now this has 2 in that cup. So that's 2 and 2. It's still 4. It's still the same number, so you increment it like that. That's the way it works. 4, 5.
Would those be zeros when you put that in there?
What's that?
Before you put this in, that's 4. Would those be zeros?
Yeah, these are zeros. Yeah, nothing represents 0. A bead represents 1. Having 2 beads would be a trinary system. You have 0, 1, and 2. We don't have that, but yeah. Okay, so that's, what is that? That's 5. Okay, it's 5. That's 6, but it's not allowed, so,
1 and the 2. 1 and the 4.
see, so that's 6. You see what I did? What we're doing is we're adding one here, and you're carrying one over and taking one out. That's what you do. It's a carry. It's kind of like in math when they say carry. Well, okay, you're actually carrying it over. Physically carrying it over.
Is that the same system Chinese use with that abacus or whatever?
I think abacus is based on the same thing. 6, so this is 7. Okay, this is 8, right? Does everyone agree that that's 8? That's 4. This has a value of 4 because it's in a different position. This has a value of 2. This has a value of 1 and 1. So that's 4, 5, 6, 7, 8. But this is not allowed, so I'm going to carry that over. That's not allowed. See, so 2 and 2 is same with 4, so I'll carry it over. Now 8. It's still 8. It hasn't changed. But, okay, so now that's 8. Does that make sense to everyone?
Yeah, it's pretty cool.
Yeah. This is the best way I found to teach people how to do. Now this would be 16. Okay, so I'll just keep counting. 9, 10, 11, 12. The cool thing about this is you don't need a whole lot of beads. Oh, I'm sorry. Yeah, I'm going to have to move that up like that. 8, 9, 10, 11, 12. So that's 12. 13, 14, carry. Right? 8, 9, 10, 11, 12, 13, 14. 15. So a 4-bit number, the highest you can go is 15. You know, that's the highest you can go. That's pretty high for 4 little cups, kind of up to 15. Now every time you add another cup, you double it. Okay? Actually, it's not really 15. It's 0 to 15, so that's 16 things you can count. You can count 0, you can count nothing, up to 15. So that's 16. This represents 32. This represents 64, 128, etc. It keeps going up. So every time you add a cup, it doubles. So it exponentially increases as an exponential number every time if you double something. If you multiply something by a fixed number, that's exponential. Now what happens? If I add one bead right here, it's going to cause a domino effect because this is all full. If I put that in there, it's going to ripple down. It's going to say, okay. Okay. That's the next one. So all these get cleared out. Okay? Okay. That's it. Well, we still have more class, but that's it for that. Play around with that at home, I would say. Actually, what I would say to do is when you go home, do your homework, get a piece of paper and draw these on your piece of paper. Okay, get a piece of paper, draw the squares. Do 1, 2, 4, 8. Get some beans or something, or whatever, rice, and count in binary like that. Practice it. You're going to be tested on it on Friday. Okay. Let's put this thing back up. Let's see that. Okay. We got a little bit of time left. Okay. So, how do we convert numbers? Learn to count in binary, page 10. We've already done that. Decimal to binary conversion, sums of powers of 2. You can convert a decimal number to by adding up powers of 2 by inspection. Okay? Let's look at the example in the book. What do they say? For example, convert 57, page 10, the very bottom. Convert 57 to binary. Now, in number systems, when you start messing around with other numbers, you start getting confused. So what we do is we do a subscript, 57 base 10. Normally, you just write 57, but that's a base 10 number, so we're going to put a base 10 under there. I don't know if you can. Let me redraw that 5. 57. So we put the 10 on the bottom to say base 10. Hey. Okay, so how can we represent this number in binary? What do you guys think?
Less than 64 if you can't do anything with that.
Okay, so you think we're going to need this
Nope.
cup? We'll call these cups. Think of it like a main color. Not going to need this cup. Are we going to need this cup?
Yes.
So we put a 1 there in 32 spot. Now how much more do we need?
25.
What do you do? Just, now that we have 1 in 37, what do we do to this number to say how much more do we need? Subtract, right? Because you've already got 32. So 32, so this gives you 25 left. So how do we get to 25? Do we put a bead in this cup?
Yes.
Okay, let's put a bead in this cup. Now we got 16, so we subtract 16.
9.
Okay. So what do we do here? We got 15, so that's 9. And then, okay, 9. What do we need to get 9? Whoop. 8. So that did a hard one for us. Usually it's a little bit easier. So now we subtract 8, that gives us 1. Do we need the 4?
No.
Do we need the 2?
No.
We need the 1.
Yes.
So your number is, how many bit number is that? How many bits do you need to represent that number?
6.
6 bits. Okay? So that is a 1001. Now what I do, I don't know if they do this in the book or not. I usually put a little dash right there because we usually separate these numbers by 4. But you don't have to do that. That's kind of advanced. We'll talk about that later. Anyway, that's 111001. And we call it a base 2. So you can put a little 2 there if you want. So that, because if you don't put the 2 there, what's going to happen? Someone's going to say, oh, well, this is a 111,001. Right? Guys, in binary, 1,000, 100, all of those terminologies don't make any sense at all. It doesn't mean anything. They don't exist. Okay? This is not... Let's do a new number. Let's say this is the binary system. Oh, that's 100. No, 100, that doesn't make any sense. There is no 100 in binary. There's no 1,000. There's no 10. The only thing that exists in binary is 0 and 1. Okay, that's it. 0 and 1. So it's 1, 0, 0. 1, 1, 1, 1, 0, 0. So, just to make sure, because I have students say, oh, that's 100. Oh, that's not 100. 100 is a completely different number. 1, 0, 0 in decimal, or in binary, they're two different things. This is 1, 0, 0 in binary, and this is 100 in decimal. In decimal, it's 1, 0, 0 base 10. And these are not equal. Those are not equal to each other. This has a value of a magnitude of what we would call 100. This has a magnitude if you convert it to what? 4. A magnitude if you convert it to our system. So they're not equal. Okay, so how do we do... of course we have the book that you guys can work on these some more. They have an example 1.3 you can work on. Okay, repeated division by 2. Repeated division by 2. I don't really use these concepts, but this is a pretty powerful thing to use, repeated division by 2. So let's say you have a number, example 46 base 10. So it's a decimal number. And we want to convert this to binary, but we don't really know how to do it. Well, what you can use is this method of repeated division by 2. So what you do is you take the number 46, you divide it by 2. What does it give you? 23, right? And what's the remainder?
1. No remainder.
So there's no remainder, so it's 0. So the remainder is 0. Because if we would have had 27 up here, it would have been 23 and a half. The half is what they mean by remainder up here, the 1. So, but it's not 47, it's 46. So it evenly divided by 2, so you got 23. So you only look at the remainder. You don't really care what this is. So this is going to be your first bit of your number, your LSB. Okay? Now you do that again. Then you take 23 and you divide that by 2. What is that going to give you? 11 and a half. So the half means that there's a remainder. We call it a remainder of 1. This is going to be your next number, your binary number. So we're creating your binary number. Okay? Binary number. 0, 1. We're kind of going this way. We can rewrite it in a minute. So now we have 11. Now if you divide that by 2, what do we get? 5.5. Right? That's 5.5. That's what that is. So that means you have a remainder. You got 1.
Why do you call that?
What's that?
Why do you call it?
It is called a remainder. If it was 10, then you would say it evenly divides. You get 5. You get nothing left over.
You know what I'm saying?
They're just calling it a remainder. It's just something that remains, right? It has to be a half because you're dividing it by 2 each time. So it's always going to either be evenly divisible or you're going to get half. That's the only 2 possibilities you're going to get. The half we're calling a remainder because there's a little bit left. So what they're saying is if you get a little bit left, it doesn't matter what you call it. You can call it a little bit left. You don't have to call it remainder. You can call it whatever you want. I mean, seriously, I'm not trying to make fun. I'm just saying that sometimes terminology can get people hooked up on terminology, but don't let it get hooked up on terminology because it's just a word that someone used. Maybe they chose a bad word. Probably they chose a bad word. I don't really like that word either. I would just say that you have a little bit left over. So, any other questions?
The remainder is always going to be 1. That sets up your binary number, right?
Your remainder, if you get something left over, it's either going to be nothing or a half. If you get something left over, then you're going to have a 1. That's going to be in your binary number. In our case, the remainder is always going to be a half, and we're going to call that, we're going to assign that to a value of 1 in your binary number. Yeah?
Why did it go from 11.5 to 10?
You throw away your remainder. Oh, I'm sorry, this did not go to 10. I was giving an example.
Okay.
I was giving an example.
I'm sorry.
10 would be an example of no remainder.
Yeah.
10 would be an example of no remainder. 11 is you have a half left over. And then if you went to 12 here, then you would go to 6. I'm just trying to show that you're either going to get 2 things. You're either going to get a remainder or no remainder. It's going to be a half or not. So 11 gives you 5.5. You got a remainder, so you give it 1. Now, let's see. 5 divided by 2 is 2.5. So you have a remainder. So you have a 1. Now here, 2 divided by 2 gives you 1. There's no remainder, so it's 0. So the way you build your number in this case is it's going to be, this is your MSB, most significant bit, 0, 1, 1, 1, 0. 0, 1, 1, 1, 0. Base 2. Base 2 system. So that's how you do it. Actually, we forgot to go. There's one other step to go. What they're saying is you have to keep going until you get nothing. So I messed that up. Keep going. You have a remainder. You have to keep going until you get no remainder. I'm sorry about that. So 1 divided by 2 gives you what? 0 with a remainder. So I would have got that problem wrong. Yeah, you have to keep going. Good thing I messed that up, right? Because now you guys won't do that on test. So you have to keep going until you have no remainder. So we have no remainder. This is 0.5, I guess you could call it. 0.5, so it has a remainder.
So that would be the most.
So this number here, you have 0. Continue the process until the quotient is 0. I'm sorry. This has to be 0. So you keep doing this process until this is 0. So, because all the way through here, look, this is 23, it was 11, 5, 2, 1 with no remainder, and finally you got down to 0 and you had a remainder. And so as soon as this quotient, we call it here, the big number is a 0, then you stop. You're done, because you can't go any further, right? You can't do 0 divided by 2. So really just keep going until you can't go any further. Actually, you could say, well, 0 divided by 2 is 0 with no remainder. So you just keep adding zeros out there. But that doesn't hurt anything. So your number would be, let's see, you got
Yeah, you'd have to have a chance with it.
0. So 0, 1. We're going to build the number from this way. This is LSB. Build the number, and then 1. And then 1, and then 0, okay, and then 1, and then 0. Now, if you keep doing this over here, what are you going to get? You're going to 0 divided by 2 is 0, the remainder is 0. Like 0, 0 divided by 2, you get 0, the remainder is 0. So you're going to keep getting zeros. That's okay. If you keep doing it, it doesn't hurt. It's still the same answer. Okay? So I would suggest is keep doing it until you start getting a bunch of zeros. Or until you get, really, this number has to be a 0. Yeah. And the way the computer and the calculator think about it is you're going to have, you always have zeros are implied out this way. Infinitely meaning zeros are always implied out to the left. All right. Well, I think we're out of time for the day. Now, the only other thing we got to cover before the quiz is fractional binary numbers. So I'm going to give you guys an assignment, and we're going to cover it the day of the quiz. We'll go over it for like 20 minutes and make sure everyone understands fractional. And hopefully you guys will work on the homework and also figure it out too. So really, on Friday, so we're going to have 20 minutes of review and help you guys make sure you got the homework right, make sure everyone's happy, make sure everyone can do it. At least 90% of everyone can do it. So you don't want to be falling behind, because 90% of people are going to be ready by Friday, and you don't want to be the one left behind, okay? So make sure you work at home on it. Okay. Okay. Now you guys did problems. Let me just make sure these are the right problems. Yeah, okay. This is the right problems. So from section 1.3, which is the section we covered today, but we didn't get the fractional numbers. Section 1.3, we're going to do problems 1.3, 1.5, 1.8, 1.10, and 1.13. Now remember, there's the examples in the book, and they give you the answers. Okay, so they give you an example, they give you the answer, they show you how to do it. So there's really no reason why you shouldn't be able to do it. It's laid out plain as, it's just right there. Everything you need to know is right there. But if you do have problems, then we are going to talk about it and go over the answers on Friday for 20 minutes before we have a quiz, and make sure everyone's going to understand it. Now, also, once you finish these problems, go ahead and let's read the next section. The priority is doing the homework and make sure that you understand it. For those of you who grasp this fully and have no problems, do the problems, then I would say go to section 1.4. If you're still struggling with this, I would say work on the quiz, because we're not going to quiz over section 1.4. The quiz is going to be section 1.1 to 1.3. So it's only going to be up to fractional binary numbers. That's it. Only up to problem 13. And it's also going to cover what we're going to work on, what we worked on in what we're going to work on in the lab tomorrow. And don't forget we have a class tomorrow too, so we can work on it during the lab tomorrow too. So I would say work on it tonight, and I'll answer any questions tomorrow first thing in the lab. If anyone has any questions, we can go over really quick fractional binary numbers. And then we'll do our lab. And please note that the quiz is also going to cover what we do in the lab. We're going to do some IC packages and how to wire those things up. So I'm going to give you a test question on how to wire up those packages. So know how to look at those packages like that 7400, 7408. Know how to, for the quiz, know how to take an IC package and to wire it up properly. Sorry I held you guys over too long.